Hello guys, in this video I am going to explain the solution of this question number 48 of chapter 8 from the books Engineering Circuit Analysis by Hayt, Kemmerly and Deriving. So the question says that for this particular circuit contains two independent sources, one is 1.2 volt and another is 50 UT milliampere, one of which is only active for t greater than 0, means since because of the presence of this ut unit step function, this source will be active only for t greater than 0, because we know that this ut it is equals to, it is 1 for t greater than 0 and it is 0 for t less than 0, right? So when it is 50 ut, it means that it is equals to 50 milliampere when t is greater than 0, otherwise it will be for t less than 0 it will be 0. So from this we can redraw this particular circuit for two cases, one for t less than 0 and another for t greater than 0. So for t less than 0, if I draw this circuit for t less than 0, then it will be something like this. And over here this current source, because for t less than 0 the current is 0, and when the current is 0 it means that the circuit is breaked, the circuit is incomplete, right? When t is equals to 0, right? So at t equals to 0 this current source will act like a open circuit, so we replace it with open circuit. This is 10 millihenry, this is 1k ohm, this is 2k ohm, this is 1k ohm, this is IL, right? Now since this particular circuit is in this condition from the last minus infinite time, so we know that when the current is stable, when the circuit is stable and there is no change in the voltage and the current going on in the circuit, then the inductor can be replaced with a short circuit, or and capacitor can be replaced with the open circuit. So under steady state this inductor will be replaced with the short circuit. So I can simply replace this with this. So at t less than 0 our circuit will simply look like this, having only the resistor, and inductor will be replaced with a short circuit, because under steady state it act like a short circuit, right? Now from this condition, if I try to determine what is this inductor current, now because this is short circuit, right? So this 1 kilo ohm is short circuited by this, so it means that the presence of this, so just I need to redraw this, so this, right? So because of this short circuit wire, this 1 kilo ohm is short circuited, means there will not be any current flowing through this. So it means I can simply remove this, right? I can remove this. So now my circuit it simply look like this. And from this circuit, if I try to determine the current IL, then it will be IL equals to 1.2 divided by, we have two registers connected in series because this is open, so simply we can remove it, right? So 2 plus 1, so it is 0.4 milliampere. Why milli? Because our registers they are in kilo ohms, right? So it means in the denominator it is kilo ohm, so our current is 1.4 milliampere. So we can say that IL at t less than 0 the current is 0.4 milliampere, or we can also say that IL 0 minus it is 0.4 milliampere. And since we know that when the current will be there, when this current source come into picture, and due to this change this inductor will come into picture, means there will be some current, some extra current may be there. So when as soon as like at t equals to 0 plus, when this current source come into picture at that particular time the current through the inductor will not change, because inductor has the property that it will try to maintain the current. So since at 0 minus the current is 0.4 milliampere, so this current will remain there at 0 plus also. So it will be 0.4 milliampere. So at 0 plus, at t equals to 0 plus, the current through the inductor will remain same, which is 0.4 milliampere. Right? Now coming to the second part, for the second condition when the t is greater than 0. So let me draw the circuit for the when the t is greater than 0. So when t is greater than 0, then this 2 kilo ohm, this 1 kilo ohm, it will remain as it is. We will have the battery of 1.2 volt, right? Then this current source, instead of 50 ut, I will write simply 50 milliampere, right? Because of this, at t greater than 0 the current is 50 milliampere, right? So this, and this inductor is we have an inductor and we have the resistor, both are connected in parallel. So I can change their positions, like I can, since they are in parallel, so we can draw either in this form, means first inductor and then resistor, or we can draw in this form, like first resistor and then inductor. So both are same thing because they are parallelly connected. So I did it purposely. The purpose will be disclosed like when I am going to solve this. So this is the condition of the circuit at t greater than 0, and this is the current IL, right? Now the question says that we need to, over here the question says that we need to obtain the expression for ILT, for IL for all t, right? Now for t less than 0, already we have determined the current through the inductor. Now we need to determine the current through this inductor. I need to determine this IL for t greater than 0. So this can be, for to determine this, simply what we need to do, whenever we get this type of a circuit, so it is always better if we somehow replace our circuit with a standard circuit which have this R L, this is IL T, and this is the voltage Vs. So if we are able to replace this big and the complex circuit into the simple circuit like this standard circuit, then it will be easy to determine the current through the inductor. So to do this, what we need to do, we will apply the Thevenin theorem. And to apply the Thevenin theorem, what is the first step? Step is that we will first replace, like if this is AB terminal, this is A, this is B, so we will first remove this inductor. So once we remove this inductor, our circuit, it will look something like this. Simply we just need to remove it. It is 1 kilo ohm, it is 1 kilo ohm, it is 2 kilo ohm, this is 1.2 volt, it is 50 milliampere, right? And this is open. So over here this will be the circuit for which we need to determine the Thevenin voltage and the Thevenin resistance. To determine the Thevenin voltage, we know that Thevenin voltage is this, that we need to determine this, right? Now to determine this VTH, simply what we need to do, we will consider, we can apply any theorem. So over here the theorem that I am applying, it is this. I will apply the nodal analysis. So to apply the nodal analysis in this circuit, we can find that there are two nodes. One node is this A and another node is this B. And for the B, we can take this VB as the reference node, means VB is equals to 0 volt. Now applying the Thevenin nodal analysis. So let this is I1, let this is I2, let this is I3. So I1 plus I2 plus I3 is equals to 0, right? Now I1 will be VA minus 1.2 upon 2. What is I2? I2 is minus 50. And what is I3? I3 is VA upon 1 plus 1 equals to 0. You can see that over here from VA, we don't not only have this 1 kilo ohm, we also have this. So we write 1 plus 1, right? And since all the registers they are in kilo ohms, so this VA minus 1.2 upon 2 will give the answer in milli ampere, because the unit of this 2 is kilo ohm, right? So now solving this, we will get like VA minus 1.2 upon 2 plus VA upon 2 equals to 50, right? So VA minus 1.2 plus VA equals to 100. So 2VA is equals to 101.2 and VA is equals to 56.50. It will be 50.6 volt. So our VA is this. Now once we get VA, our what we need to determine, we need to determine this VTH. And what is VTH? VTH is the voltage drop across this 1 kilo ohm. It is the voltage drop across this, right? So first of all, I need to determine this I3 current, the current that is flowing through this 1 kilo ohm. So the current that is flowing through this 1 kilo ohm, it is this VA upon 2. So the current that is flowing through this 1 kilo ohm, through this, let it be 1K. So it will be like VA upon 1 plus 1, right? So VA we have determined VA is 50.6. So 50.6 upon 2. So IK it is 25.3 volt. So we get IK as 25.3 volt. And then what will be VTH? VTH is I into 1K. So it will be, this current will be milliampere, right? Because it is IK and in the denominator we have kilo ohm. So the answer will be this, milliampere. Now VTH will be 1 IK into 1 kilo ohm, I into 1 kilo ohm. So it is 1 into 25.3. So our VTH, it is 25.3 volt. So this is our Thevenin voltage, or we can put it over here, VTH. It is 25.3 volt. Our L, it is given this. Now we need to determine the Thevenin resistance. Now to determine the Thevenin resistance, we know that if in this circuit, let me remove the irrelevant things. Okay, so we know the concept of determining the Thevenin resistance. So to determine the Thevenin resistance, simply what we have to do, we need to remove all the independent sources. So we will replace this voltage source with a short circuit, and we will replace this current source with the open circuit. So if I do that, let me do it over itself. So this will be removed, right? And over here, this voltage source, it will be replaced with the short circuit. So my circuit, it will look something like this, right? And now I need to determine the Thevenin resistance from this terminal. Now from this terminal AB, the Thevenin resistance over here, this 2, this and this, they are in series, so they will become 2 plus 1, they will become 3 kilo ohm, right? Now this 3 kilo ohm, it is in parallel with 1 kilo ohm. So it means our Thevenin resistance, it will be 3 into 1 upon 3 plus 1. So it is 3 upon 4. So it is 0.75 kilo ohm. So our Thevenin resistance, it is 0.75 kilo ohm. So over here our circuit, now it just have one voltage, one resistance and one inductor. And for this particular circuit, we know that the equation, the for this particular, we can determine the current ILT using the concept of the complementary function and the particular integral of the differential equation. And the solution is like this, that we have this q by p plus a e minus p by t, right? Over here our p it is r by l, our q it is v naught by l, right? So our ILT, it will be given as like q, our substituting this q and p value in this equation, we will get ILT as v naught by r plus a e power minus p is r by l t, right? Now over here, so this is the equation of the, this is the inductor equation. Now in this equation we have one unknown, which is a, right? Now to determine this a, what we need to do, we need to use the initial condition. What is the initial condition? Initial condition is, we have determined over here. The initial condition is that at IL at t equals to 0 plus, the inductor current is 0.4 milliampere. So substituting using this thing over here, so over here we will get like IL 0 plus, the value we get is 0.4 milliampere, right? Is equals to v naught upon r. Now what is v naught? Over here v naught upon r plus a e power minus r by l, and it is 0, right? So we get 0.4 milliampere equals to v naught upon r plus a, right? Because this term it will become 1, right? So from this we get a is equals to 0.4 minus v naught upon r. Now what is this v naught upon r? To over here from our circuit, this v naught, it is this vth. So this can be rewritten as ILT is equals to v naught is 25.6, r is our 0.75 kilo, so 0.75 plus a e power minus 0.75 upon l is 10 upon t, and it is 10 milli. We need to write it as 0.75 into 10 power 3 upon 10 into 10 power, it is kilo ohm, it is milli henry. So this, right? So and solving this we will get like 25.6, or we will get like instead of this 25.3, not 6, it is 3, right? So 25.3 upon 0.75, this will be, this is 3, this is 4, and this 3, and this we will get 8.43. So 8.43 into 4, we will get something like 12, 1 carry 16, 12, 1 carry 16, 17.33. So 33.72. So it is 33.72 plus a e power. Now this is plus 3, it is minus 3. So if we take this on this 10 into 10 power minus 3, it is 10 power minus 2. And if we take this in the numerator, so we will get 10 power plus 5. So this will be minus 75000 t. So our ILT, it is this, right? So instead of like over here now, if I substitute let me instead of this, because otherwise I need to resolve it again. So instead of this, if I substitute like over here, just a minute, let me erase this. So over here, if I now substitute the value of 0 plus, which we get it as 0.4. Over here, remember unit is milliampere. Why milliampere? Because over here we have divided it by 0.75 kilo ohms, and since it is kilo ohms, so the unit is milliampere. So now using this condition, what we will get? We will get 33.72 plus a e power minus 75000 into 0 milliampere, right? And this expression, since it is multiplying with 0, so this expression will become e power 0 means 1. So we will get 0.4 equals to 33.72 plus a, right? And it means that it will be 33 minus 33.32. A is minus 33 point. So our inductor current it expression, it is this 33.72 minus 33.32 e power minus 75,000 t, so milliampere. So this is our expression. This is our expression for the current, inductor current at t greater than 0, and for inductor current is equals to 0.4 for t less than 0. So this is our overall expression for the inductor current, and this is the first part of the question that we need to determine. That the first part says that we need to determine the expression of inductor current that is valid for all t. So this we have calculated. Next we need to calculate the inductor current at 3 t's, at t equals to 10 microsecond, 20 microsecond and 50 microsecond. So over here, simply like the expression that we have obtained, we just have to substitute the values. So the expression that we got, it is just a minute, so it is this. So in the b part, we will simply substitute this. In this equation we will substitute 10 microsecond, right? So if you substitute the value in this expression, minus 75,000 into 10 into microsecond, since it is microsecond, so you need to put 10 power minus 6, right, milliampere. So the answer to this, the answer that you will get, it will be 17.99 milliampere. Similarly, if you evaluate for 20 microsecond, you will get the answer as 26.29 milliampere, and for 50 microsecond, you will get the answer as 32.95 milliampere, right? So this is the answer to the second part of the question. So this is the solution to this particular question 48 of the book, of the chapter 8 of this book. If you have any doubt, you can put it in a comment box. Do subscribe my channel and share this video with your friends and colleagues. Thank you.